Okay, thank you for the introduction, and we will give you an overview today what's all about software-defined networking thing and OpenFlow, which is all over the place in networking at the moment for about 2 years, and it's an emerging technology with, which enables you to program your network. And what it means, I will show you in the next slides. And we have made a presentation today where we go through the business stuff first, a few slides, but I think we are very technical around here, and we have another slide set, which is done by Andreas, about implementation based on Erlang, of course. So OpenFlow started in 2008 at Stanford, and at this time, there was a need for slicing your campus network into different areas where you can make some experiments for networking. Because the problem with networking was at this edge that the devices deployed on campus networks or enterprise networks or even carrier networks are very, very static. And the innovation, it's quite slow, and that's for a reason, because a network device has to be stable, has to be tested, and so on. But all other software industry or other technologies like virtualization has stepped up very, very fast. But networking still was some kind of slow, and the Stanford team asked themselves how we can innovate the wiring closet, the rack, and the switches. And after a while, they come up with this OpenFlow thing, which basically it's a technology, it's an API, and you can use with any programming language. And a bit later, the ONF was founded, basically last year. And as you can see, the adoption of OpenFlow, software-defined networking, it's really, really big. Nearly every networking vendor has joined the ONF, and quite a lot of software companies and hardware companies as well. And there's another website on the right-hand side, which is the OpenFlow Hub site, where projects are listed. But if you look around in GitHub, an example, you will see for nearly every interesting programming language is OpenFlow activity today. So what's the difference on software-defined networking? Usually in today's networking devices, all the functionality is local to the device, regardless how big it is, from the small tabletop switch up to the big router. The functionality, it's built into the device, and you can configure existing functionality, but you can't expose the functionality or the network functionality directly to an external controller. And that's what OpenFlow and SDN is promising. You have your forwarding plane, relatively dumb, and you expose forwarding as a concept in networking to a controller. I think we all know some use cases how to change network settings, the configurations of your network as an application developer or as an administrator of an application. You have to ask your network admins to do something. There are some ways of doing this automatically, and there are some ways of doing this dynamically, but you always configure your network. That's the usual admin, and doing this on the command line for a Cisco router, an example. That's getting a little bit more challenging if you have a couple of routers. So they started years ago to do some CLI automation. That was the funny days in the 90s where you write expect scripts to telnet into the device and try to do something automatically. This usually fails if the CLI syntax has changed for next firmware version and so on. But was the very first step to automate configuration management. Then we come up with other approaches like netconf, SNMP, or other element management systems, which go into the devices and configure quite a lot of devices. The problem with SNMP was today is only read-only, so you read metrics or something like this, but you not really configure the devices via SNMP. There is already something like software-defined networking in huge carrier networks. In a carrier network, a resource like bandwidth from A to B needs to be is requested by an application. And there's a way already to push configuration changes or changes of the network behavior to the network by protocols like radius and diameter. But this is mainly to 3G network provider or even carrier network. It's overly complex, and you have not many vendors doing that. In a typical enterprise switch, diameter stuff is not available at all. The conclusion for that is, even today, you always configure existing functionality of a switch or a router, and there's no common API to program the network functionality, because even you have a compressive API, the API always exposes the functionality already exists on the router. You can't change a routing protocol, or you can't implement a routing protocol this way. What OpenFlow promises is to have a very, very basic API about forwarding. And that's three elements here. You have a rule or a match, which can match on all packets in an Ethernet frame. If it matches, you have an action to do something with that. And the action can be to pop and push parts of the packets, like the tags, or send the packet to the controller to further analysis, and so on. And with this basic functionality, you can do what you want with your network packet. But the network packet forwarding, it's still in the hardware device and is not sent to the user land and a Linux kernel, an example. It's still at wire speed. So, and we are running Erlang-based OpenFlow controller for quite a while now. We started 1.5 years ago to develop something like that, and launched this year a machine-to-machine network based on OpenFlow, which builds a network above 3G networks around the globe and makes some very, very compressive policy controls. You have virtual groups, you can group devices together. You have a lot of network address translation functionality between devices, and all this fine granular management is based on an OpenFlow controller. And there's another project at the moment running where we're using the same technology, which is a proof of concept implementation of a controller which acts as a PPPoE terminator in a carrier network, but not sending the traffic back to a central, highly expensive, huge BRAS box. The actual PPP termination, it's done out to the edge on the switches directly, and the PPP frames are terminated quite early and forwarded as normal IP over Ethernet frames through the network, which is much more efficient, much faster, and you eliminate the huge BRAS, which is very, very costly usually. And as a side effect, you get a multicast replication further out to the edge, so you don't send IPTV traffic in this example through the whole network back and forward. You terminate this very early on the switch of the access network where the customer is connected. So being on the Erlang conference, of course, we will present how we do it and what we've done here, and that's a part of Andreas. So we built an OpenFlow controller in Erlang, which is modeled like most of the other controllers, but I think Andreas can talk about that much better than me. So.
Hi. Flower is our platform for building a building any kind or any number of OpenFlow controllers in Erlang. Now, let's get started with the basic difference from a classical switch versus software-defined networking. Holger already said a lot of things about that, so let me repeat a few things. Now, with a classical network switch, you got a static control path. You configure the thing, and then it works the way it's supposed to be. You can slice your network with a number of mechanisms like VLANs, filters. You can have AAA mechanisms allowing clients on the network or denying them on the network. But still, the decisions you can make on the packet are limited. You can match on MAC addresses, you can match on VLAN tags and quality of service tags, but that's mostly it. Some layer 3 switches can do a bit more, but they still only look at very limited part of the packet itself to make the forwarding decision. And one of the major things is when a forwarding decision for a specific type of flow or a specific type of packet has been made, it can usually not be altered while this flow is active. So the next flow might get a new decision, but the current flow, the way it's forwarded, it will stay that way. So for a normal layer 2 switch, the processing is very, very simple. Basically, it gets a packet coming in through one port. It learns the source MAC address is located on that port. So it might know where the destination MAC address is located. So it basically forwards the packet to that port. Or if it doesn't know where the MAC address is located, it simply floats it on all the ports, hoping that somebody will do something with the packet. Now, that leads to a number of different interesting questions. Now, if a MAC address moves from port to port, like if you have a VM being migrated to a different physical host, how does a switch learn that the MAC address has been moved? There are a number of existing mechanisms, but they all have the drawback that the host has to be proactive. He has to signal that he has been moved. They also get certain number of delays. Then how can I slice a switch in different parts? For example, if I have a large distribution network going out to some customer homes, I might want to put different carriers on them, or they might want to share the same share the same distribution network. How can I isolate them from each other? With a normal switch, I do have mechanisms like VLANs, but they need to be configured. They're not dynamically, and basically they cannot be automated. People have to go in, an administrator has to go in, change the configuration, and that takes time and effort. And then, especially if I have infrastructures like Ethernet to the home or fiber to the home, I want a uniform infrastructure, but I still want to isolate my clients from each other. Again, I could use VLANs or PPPoE, but all this brings either additional traffic in forms of headers onto the network, or again, I have the configuration problem. Now, with the big promise of this software-defined network is that I can decouple all this control plane things from my actual forwarding. But I still need to get the decision to the forwarding plane, and I have an open, well-defined API for that. The other thing is I can have one central instance controlling a large network of different boxes. I could have a distribution network with 1,000 switches and still have a centralized, redundant instance controlling them all, which means that I also have a global view onto my network, which makes it much easier to actually, for example, move a MAC address from one port to the other. And I cannot only move it within the same switch, I can move it wherever I want within my network. So even large geographical distances make no difference anymore. The other thing is I can match on everything in my packet. I can take the classical things, but I can go even into the payload of the packet if I want to. And the other thing is, in a normal layer 2 forwarding thing, I cannot really alter a packet. I might be able to do a limited amount of NAT, But with a software-defined network, I could change anything within the packet. Mostly, this should not be restricted to traffic or payload headers, because altering the payload of the packet itself can be tricky, but still. So where we had the monolithic switch before, that we were doing everything on its own, we now get a much more modular approach, where the switch basically has specialized hardware for the data path, for the forwarding, so that can forward at line speed, like 10 gig or more, or whatever. It got a control path thing that actually propagates the the API decisions onto the hardware, and we have the externally accessible API, which then talks to the controller, and the controller can talk to any number of those switches. Yeah, again, we got the flexible matching. We can learn MAC addresses over multiple switches and all those things. Now, we have already talked a lot of OpenFlow. What really is OpenFlow? It's actually two things. It's a protocol specification, with the last released version being 1.1. And it's also a reference implementation of a software-defined network. The reference implementation is currently a Linux kernel module that is implementing a data path, the forwarding instance, but it's also a sample implementation of on an FPGA board, where you can actually do 1 gigabit line speed forwarding on a normal PC platform. It's also the basis for several existing commercial OpenFlow implementations. It's not quite clear whether OpenFlow or OpenVSwitch or some own implementation by the vendors are used there, but some have stated that they are using the OpenFlow implementation. Normally in an OpenFlow enabled switch, if a new flow comes in, this is what might happen. You get the notification that there's a new unknown packet coming in. The OpenFlow controller then has to make a decision telling the switch what to do with the flow in form of a flow add message. Later on, while the flow is still active, it might decide to modify the flow, to simply forward the traffic to a different port, completely block it, whatever it wants. Then, after the flow has been idle for a certain time, obviously the switch or the OpenFlow data path element will notify the controller that the flow has expired, so it can be removed from any kind of database that there might be. Now, another OpenFlow implementation is OpenVSwitch. This implementation was originally based on the OpenFlow reference implementation, but has since moved on a lot. Like the OpenFlow reference implementation, it has a Linux kernel data path element. It has a controller written in C++, and it has a configuration database. And that is really what sets it aside from the OpenFlow implementation that has no configuration database. There you have to manually add and remove ports from your forwarding path. With OpenVSwitch, that part can be automated through the database. Like the OpenFlow implementation, it can act as a controller to an OpenFlow-enabled hardware switch, and it is used as the software switch in Xen, or it will be in the next version anyway. Before that, there was a mix of bridging and things like this, but now with the new infrastructure, they will be able to much easier move virtual machines across physical hosts as well. It also has support for a lot of the standard management interfaces you find in normal switches, like NetFlow, RSPAN for monitoring. Has also link aggregation, which is one of the major differences to OpenFlow. And spanning tree, of course, all those things. You also got some extensions over the standard OpenFlow protocol, which gives you much more flexible matching, where you can kind of write a mini program to actually control the forwarding decision. Not only have the static match, but kind of load a register, do a decision based on that, and then have conditional jumps and this kind of things. Now, on to our nice platform, Flower, which is a play on Flow and Erlang. Now, this is a platform to actually build an OpenFlow controller based on Erlang. Other controller or other development environments for other languages exist. There, for example, is Nox, which started out with a lot of Python, but since has moved on to C and C++. There are also several Java implementations where you can build your Flow controller with. Now, the major goal was here that someone who wants to implement a controller can concentrate on its switch and flow logic and doesn't have to deal with all the things surrounding that, like packet decoding, encoding, protocol decoding, or the other management protocols like spanning tree or those kind of things. So what we provide is the protocol connection data abstraction, so decoding, as I said, and a number of tools and algorithms you need usually in a typical switch. So why do it in Erlang? Well, you probably know why. Just a few things, but of course, binary matching, fault isolation, concurrency. I like the fault isolation point actually the most, because it's so easy to get the decoding of a certain payload packet wrong, and this really saves your life there. So this is the big overview picture what Flower looks like. You obviously got your connection abstraction, which deals with talking to the actual hardware or to the actual software implementation of an OpenFlow switch. The dispatcher that distributes all the interesting messages to your controller, so your controller doesn't have to deal with everything that comes in, but just the things that he's interested in. You might have a controller that's only interested in doing spanning tree, so you can actually register only for spanning tree messages. And then obviously all the support library functions, like a library for a network information base. That's something like for example, a routing table you would build with. MacLearning database, the flow decoder, which actually can decode. It's not about protocol decoding, but decoding a payload packet in its layer 3 and possibly layer 4 information. And then pure packet de-encoder, that is sometimes your controller needs to send or decode ARP packets, ICMP packets to learn something about the network infrastructure, and this part deals with that. Now, if you write a controller based on the Flower platform, this is how the components will work together. You got your flow dispatcher, which is routing the messages to the controller, the Flower data path module, which is an abstraction of the real hardware, which also hides the differences within the hardware. Your hardware might implement different capabilities. Now, the data path element, or the Flower data path element, encapsulates that so that you don't have to think about all the different capabilities that your switch might have. You simply can tell it, do that for me, and the Flower data path element will translate that into the right command for it. And Flower connection, which is basically just doing the transport mechanism. Yeah, this is again what I just said. One thing, the controllers are chainable. So once your controller has come to a decision, or it might send off an event, and the other controllers can react on that. So you can have, again, a basic controller doing one thing of the network, and what he has learned, another controller might extend upon that. The data path element that, as I said, abstracts the real OpenFlow element, manages the connection setup, and those things. Now, the OpenFlow protocol is defined in terms of C structs. So there's no formal specification that tells you how long a field is or whatever. It just gives you a C struct, and you have to live with that. Now, the packet decoder more or less translates this one-to-one in a Erlang structure, which might look like this, which is actually a switch feature exchange. Network information base. Well, as I said, it's used for building routing tables, for example, where you have not only an IP address to look up, but a prefix length as well. So it's not just a key value-based lookups, but a bit more. MAC learning database, the key thing is here that some MAC addresses are special, so you don't learn them, or you learn them in special ways. And also those addresses do expire, because a client might simply disconnect from your network or disappear from the network without you ever knowing. So you actually give them an expiry. Packet decoder, well, it extracts all the necessary and interesting details about the packet you might have got. And the packet D and encoder, which gives you, for example, it helps you constructing ICMP and R packets easily and without much effort. Now, OpenFlow deals with matches. So if you tell your switch here, this is the information I have the flow, you have to always to specify a match. This is what such a match would look like. Now you can construct them by hand, but it's usually a bit complex doing or setting all the values. So what Flower gives you instead, you give it a flow, which is basically decoded from the incoming packet, and tell it what you want to match on, which with the encode OFP match, and it will construct you then the complex match structure. So it's a two-stage process, so greatly simplifying the construction of those matches. We have one controller implementation that we have included in Flower, which is the Flower Simple switch. It's a simple, very easy, very simple layer 2 learning switch. And if you remove all the boilerplate code, it's just 50 lines of code. All the rest is covered by the libraries and by Flower itself. Now our production switch, which is part, or the main part of the SCG, contains about 1,000 to 1,100 lines of code. There's a lot of boilerplate code, like starting processes, this kind of things. So it's a bit hard to count all this. But this is a real layer 3 switch, and actually implements something like a control matrix where you have all your clients that you know in a matrix, and then can specify exactly which client is allowed to which other client. And you can change that at runtime with AAA or with a simple API call. That is currently used in a machine-to-machine communication where you have overlapping groupings. So it's basically that you have multiple manufacturers delivering those machines to multiple clients, but the manufacturers still need access to all their own systems or to the systems they build, and the clients have systems from different manufacturers and they want access to all their machines. So you have those overlaying groupings, and that is realized through this matrix configuration. Well, nothing is perfect, neither is Flower. So IPv6 support is currently mostly missing. For the current products, we didn't need it, but it's coming, I hope. The MAC learning database, yes, that is a rather simple implementation currently, so it doesn't scale at all. The difference between doing a MAC learning and doing just forwarding is about a factor of 100 at the moment, so it's really terrible. But we have some ideas how we will fix that. Now the network information base needs to be extended for v6, and then there are also some other features that we would like in there. So this next month should bring this as well. Yeah, well, the last point is mostly the most important, the documentation. If you look at the check-ins to the project, you will see that there have been some additions in the last days, but many more are needed. So this is going to come as well. Load distribution, well, that is an interesting thing. Building a distributed controller requires a lot of things. You have to sync state between it. You have to distribute your incoming packets between the controllers. And even if you are not doing a distributed thing, you might want to distribute the incoming packet decisions to different controller instances. Now, at the moment, this is a pure round-robin thing. For a more complex implementation, that will be not enough. So there's some work needed as well. Now, you can get Flower on GitHub if you want to experiment with software-defined networks. And contributions are welcome, as always. Well, that's it. Thank you. Questions?
Are you using any specific hardware as a data path? Because I've been looking into OpenFlow and being able to do basically the same but using Python and other libraries. But I got interested if you have any specific hardware or if you are doing it only with OpenFlow switch.
Well, our current product is doing it all in software. But there is, I think it was released a few weeks ago, HP released a commercial version for some of the bigger switches. So you can run it on their hardware. And there's also this one, I think it's a PCI Express board, which has an FPGA on it, and 2 gig or 10 gig Ethernet ports. You can run a optimized OpenFlow implementation on that.
Are there any security considerations given that OpenFlow gives me the ability to manipulate everything in the packet?
Well, you have to trust your OpenFlow controller. The communication between the actual data path and the controller can be encrypted using SSL and can be secured with certificates and everything. But as far as your payload manipulation goes, you simply have to trust that your controller is doing the right thing. Yes?
How do you guarantee the connectivity between the OpenFlow controller and every physical switch it is supposed to manage in the event of, let's say, link failure? In the traditional networks, the span tree algorithm reconfigures the span tree automatically among the switches. But now you have to rely on an external controller to fix the faults in the switches. And again, the OpenFlow controller is depending upon the switches to provide connectivity to itself. So it's kind of, how do you guarantee the connectivity?
With OpenFlow itself, there's nothing in the spec that gives you any failover capabilities. Open vSwitch has implemented that, so you can have primary and secondary standby controllers. So you can, well, you have to exchange your actual switch state between those then. As for the switch itself, if it loses the connection to the controller, for all the existing products, you can either configure it to close completely or fall back to a normal switch mode. But once it loses the connection to the controller, you just don't have any control about it anymore. Some of the implementations do have the ability to fall back to a local instance of the controller, or actually each OpenFlow controller can be a controller and a consumer, or a client, or to another controller. So you actually can chain them as well. That's actually what's happening on the hardware or on the real switch itself anyway, you will have a small controller there that then talks to your centralized controller, which then might talk to the another instance. And you always have the choice to just continue with the information you have, just not establishing new flows. So you basically keep running what you have until you get reconnected to your central instance. Any more?
Are there any other ones? Okay. Thank you very much, guys.
Thank you. Thank you.